90377 Sedna is a large, trans-Neptunian object that was, as of 2012, about 3 times as far from the Sun as Neptune. Spectroscopy has revealed that Sedna's surface composition is similar to that of some other trans-Neptunian objects, being largely a mixture of water, methane, and nitrogen ices with tholins. Its surface is one of the reddest in the solar system. It is probably a dwarf planet. For most of its orbit, it is even farther from the Sun than at present, with its aphelion estimated at 937 astronomical units, 31 times Neptune's distance, making it one of the most distant known objects in the solar system other than long-period comets. Sedna's exceptionally long and elongated orbit, taking approximately 11,400 years to complete, and distant point of closest approach to the Sun, at 76 AU, have led to much speculation about its origin. The Minor Planet Center currently places Sedna in the scattered disk, a group of objects sent into highly elongated orbits by the gravitational influence of Neptune. However, this classification has been contested, because Sedna never comes close enough to Neptune to have been scattered by it, leading some astronomers to conclude that it is in fact the first known member of the inner Oort cloud. Others speculate that it might have been tugged into its current orbit by a passing star, perhaps one within the Sun's birth cluster, an open cluster, or even that it was captured from another star system. Another hypothesis suggests that its orbit may be evidence for a large planet beyond the orbit of Neptune. Astronomer Michael E. Brown, co-discoverer of Sedna and the dwarf planets Eris, Haumea, and Makemake, believes it to be the most scientifically important trans-Neptunian object found to date, because understanding its unusual orbit is likely to yield valuable information about the origin and early evolution of the solar system. Discovery and naming. Sedna, provisionally designated 2003 VB12, was discovered by Mike Brown, Caltech, Chad Trujillo, Gemini Observatory, and David Rabinowitz, Yale University, on November 14, 2003. The discovery formed part of a survey begun in 2001 with the Samuel Ocean Telescope at Palomar Observatory near San Diego, California, using Yale's 160-megapixel Palomar Quest camera. On that day, an object was observed to move by 4.6 arcseconds over 3.1 hours relative to stars, which indicated that its distance was about 100 AU. Follow-up observations in November through December of 2003 with the SMARTS telescope at Cerro Tololo Inter-American Observatory in Chile, as well as with the Tenegra 4 telescope at the W.M. Keck Observatory in Hawaii, revealed that the object was moving along a distant, highly eccentric orbit. Later, the object was identified on older pre-Covery images made by the Samuel Ocean Telescope, as well as on images from the Near-Earth Asteroid Tracking Consortium. These previous positions expanded its known orbital arc and allowed a more precise calculation of its orbit. Our newly discovered object is the coldest, most distant place known in the solar system, said Mike Brown on his website. So we feel it is appropriate to name it in honor of Sedna, the Intuit goddess of the sea, who is thought to live at the bottom of the frigid Arctic Ocean. Brown also suggested to the International Astronomical Union's IAU Minor Planet Center that any future objects discovered in Sedna's orbital region should also be named after entities in Arctic mythologies. The team made the name Sedna public before the object had been officially numbered. Brian Marsden, the head of the Minor Planet Center, said that such an action was a violation of protocol, and that some members of the IAU might vote against it. However, no objection was raised to the name, and no competing names were suggested. The IAU's Committee on Small Body Nomenclature formally accepted the name in September 2004, and also considered that, in similar cases of extraordinary interest, it might, in the future, allow names to be announced before they were officially numbered. Orbit and rotation. Sedna has the longest orbital period of any known large object in the solar system, calculated at around 11,400 years. Its orbit is extremely eccentric, with an aphelion estimated at 937 AU and a perihelion at about 76 AU, the most distant perihelion ever observed for any solar system object. At its discovery, it was 89.6 AU from the Sun, approaching perihelion, and was the most distant object in the solar system yet observed. Eris was later detected by the same survey at 97 AU. Although the orbits of some long-period comets extend farther than that of Sedna, they are too dim to be discovered except when approaching perihelion in the inner solar system. Even as Sedna nears its perihelion in mid-2076, the Sun would appear merely as a very bright star in its sky, only 100 times brighter than a full moon on Earth. For comparison, the Sun appears from Earth to be roughly 400,000 times brighter than the full moon, and too far away to be visible as a disk to the naked eye. When first discovered, Sedna was thought to have an unusually long rotational period, 20 to 50 days. It was initially speculated that Sedna's rotation was slowed by the gravitational pull of a large binary companion, similar to Pluto's moon Charon. A search for such a satellite by the Hubble Space Telescope in March 2004 found nothing, and subsequent measurements from the MMT telescope suggest a much shorter rotation period of about 10 hours, rather typical for a body of its size. Physical characteristics. Sedna has a V-band absolute magnitude, H, of about 1.8, and it is estimated to have an albedo of about 0.32, thus giving it a diameter of approximately 1,000 kilometers. At the time of its discovery, it was the intrinsically brightest object found in the solar system since Pluto in 1930. In 2004, the discoverers placed an upper limit of 1,800 kilometers on its diameter, but by 2007 this was revised downward to less than 1,600 kilometers, after observation by the Spitzer Space Telescope. In 2012, measurements from the Herschel Space Observatory suggested that Sedna's diameter was 995 plus or minus 80 kilometers, which would make it smaller than Pluto's moon Charon. Because Sedna has no known moons, determining its mass is currently impossible without sending a space probe. However, if the above estimates for its diameter are coupled with Pluto's density of 2.0 grams per centimeters cubed, the resultant estimated mass range is about 1 times 10 to the 21st kilograms. Observations from the SMARTS telescope show that in visible light Sedna is one of the reddest objects in the solar system, nearly as red as Mars. Chad Trujillo and his colleagues suggest that Sedna's dark red color is caused by a surface coating of hydrocarbon sludge, or tholin, formed from simpler organic compounds after long exposure to ultraviolet radiation. Its surface is homogeneous in color and spectrum. This may be because Sedna, unlike objects nearer the Sun, is rarely impacted by other bodies, which would expose bright patches of fresh icy material like that on 8405 Asbolus. Sedna and two other very distant objects, 87269 2000 0067 and 2006 SQ372, share their color with outer classical Kuiper belt objects and the Centaur 5145 Tholins, suggesting a similar region of origin. Trujillo and colleagues have placed upper limits in Sedna's surface composition of 60% for methane ice and 70% for water ice. The presence of methane further supports the existence of tholins on Sedna's surface, because they are produced by irradiation of methane. Barucci and colleagues compared Sedna's spectrum with that of Triton, and detected weak absorption bands belonging to methane and nitrogen ices. From these observations, they suggested the following model of the surface: 24% Triton-type tholins, 7% amorphous carbon, 10% nitrogen, 26% methanol, and 33% methane. The detection of methane and water ices was confirmed in 2006 by Spitzer Space Telescope mid-infrared photometry. The presence of nitrogen on the surface suggests the possibility that, at least for a short time, Sedna may possess an atmosphere. During a 200-year period near perihelion, the maximum temperature on Sedna should exceed 35.6 Kelvin, negative 237.6 Celsius. The transition temperature between alpha phase solid N2 and the beta phase seen on Triton. At 38 Kelvin, the N2 vapor pressure would be 14 microbar, 0.000014 atmospheres. However, its deep red spectral slope is indicative of high concentrations of organic material on its surface, and its weak methane absorption bands indicate that methane on Sedna's surface is ancient, rather than freshly deposited. This means that Sedna is too cold for methane to evaporate from its surface and then fall back as snow, which happens on Triton and probably on Pluto. Models of internal heating via radioactive decay suggest that Sedna might be capable of supporting a subsurface ocean of liquid water. Origin. In their paper announcing the discovery of Sedna, Mike Brown and his colleagues described it as the first observed body belonging to the Oort cloud, the hypothetical cloud of comets thought to exist nearly a light year from the Sun. They observed that unlike scattered disk objects such as Eris, Sedna's perihelion, 76 AU, is too distant for it to have been scattered by the gravitational influence of Neptune. Because it is a great deal closer to the Sun than was expected for an Oort cloud object, and has an inclination roughly in line with the planets and the Kuiper belt, they described the planetoid as being an inner Oort cloud object, situated in the disk reaching from the Kuiper belt to the spherical part of the cloud. If Sedna formed in its current location, the Sun's original protoplanetary disk must have extended as far as 75 AU into space. Also, Sedna's initial orbit must have been approximately circular, otherwise its formation by the accretion of smaller bodies into a hole would not have been possible, because the large relative velocities between planetesimals would have been too disruptive. Therefore, it must have been tugged into its current eccentric orbit by a gravitational interaction with another body. In their initial paper, Brown, Rabinowitz, and colleagues suggested three possible candidates for the perturbing body: an unseen planet beyond the Kuiper belt, a single passing star, or one of the young stars embedded with the Sun in the stellar cluster in which it was formed. Mike Brown and his team favored the hypothesis that Sedna was lifted into its current orbit by a star from the Sun's birth cluster, arguing that Sedna's aphelion of about 1000 AU, which is relatively close compared to those of long-period comets, is not distant enough to be affected by passing stars at their current distances from the Sun. They propose that Sedna's orbit is best explained by the Sun having formed in an open cluster of several stars that gradually disassociated over time. That hypothesis has also been advanced by both Alessandro Morbidelli and Scott J. Kenyon. Computer simulations by Giulio A. Fernandez and Adrian Brunini suggest that multiple close passes by young stars in such a cluster would pull many objects into Sedna-like orbits. A study by Morbidelli and Hal Levison suggested that the most likely explanation for Sedna's orbit was that it had been perturbed by a close, approximately 800 AU, pass by another star in the first 100 million years or so of the solar system's existence. The trans-Neptunian planet hypothesis has been advanced in several forms by a number of astronomers, including Rodney Gomez and Patrick Laikawaka. One scenario involves perturbations of Sedna's orbit by a hypothetical planetary-sized body in the inner Oort cloud. Recent simulations show that Sedna's orbital traits could be explained by perturbations by a Neptune mass object at 2000 AU or less, a Jupiter mass at 5000 AU, or even an Earth mass object at 1000 AU. Computer simulations by Patrick Lykauka have suggested that Sedna's orbit may have been caused by a body roughly the size of Earth, ejected outward by Neptune early in the solar system's formation, and currently in an elongated orbit between 80 and 170 AU from the Sun. Mike Brown's various sky surveys have not detected any Earth-size objects out to a distance of about 100 AU. However, it is possible that such an object may have been scattered out of the solar system after the formation of the inner Oort cloud. It has been suggested that Sedna's orbit is the result of influence by a large binary companion to the Sun, thousands of AU distant. One such hypothetical companion is Nemesis, a dim companion to the Sun that has been proposed to be responsible for the supposed periodicity of mass extinctions on Earth from cometary impacts, the lunar impact record, and the common orbital elements of a number of long-period comets. However, to date no direct evidence of Nemesis has been found, and many lines of evidence, such as crater counts, have thrown his existence into doubt. John J. Matisse and Daniel P. Whitmire, longtime proponents of the possibility of a wide binary companion to the Sun, have suggested that an object of 5 times the mass of Jupiter, lying at roughly 7,850 AU from the Sun, could produce a body in Sedna's orbit. Morbidelli and Scott J. Kenyon have also suggested that Sedna did not originate in the solar system, but was captured by the Sun from a passing extrasolar planetary system, specifically that of a brown dwarf about 1/20th the mass of the Sun. Population. Sedna's highly elliptical orbit means that the probability of its detection was roughly 1 in 80, suggesting that, unless its discovery was a fluke, another 40 through 120 Sedna-sized objects would exist within its region. Another object, 2000 CR105, has a similar but less extreme orbit. It has a perihelion of 44.3 AU, an aphelion of 394 AU, and an orbital period of 3,240 years. It may have been affected by the same processes as Sedna. Each of the proposed mechanisms for Sedna's extreme orbit would leave a distinct mark on the structure and dynamics of any wider population. If a trans-Neptunian planet was responsible, all such objects would share roughly the same perihelion, 80 AU. If Sedna were captured from another planetary system that rotated in the same direction as the solar system, then Sedna's population would all possess relatively low inclinations and possess semi-major axes ranging from 100 to 500 AU. If it rotated in the opposite direction, then 2 populations would form, one with low inclinations and one with high. The gravity of perturbing stars would produce a wide variety of perihelia and inclinations, each dependent on the number and angle of such encounters. Gaining a larger sample of such objects could therefore help in determining which scenario is most likely. I call Sedna a fossil record of the earliest solar system, said Brown in 2006. Eventually, when other fossil records are found, Sedna will help tell us how the Sun formed, and the number of stars that were close to the Sun when it formed. A 2007 through 2008 survey by Brown, Rabinowitz, and Megan Schwamb attempted to locate another member of Sedna's hypothetical population, although the survey was sensitive to movement out to 1000 AU, and discovered the likely dwarf planet 2007 OR10, it detected no new bodies in Sedna-like orbits. Subsequent simulations incorporating the new data suggested about 40 Sedna-size objects probably exist in this region. Classification. The Minor Planet Center, which officially catalogs the objects in the solar system, classifies Sedna as a scattered object. However, this grouping is heavily questioned, and many astronomers have suggested that it, together with a few other objects, e.g. 2000 CR105, be placed in a new category of distant objects named Extended Scattered Disk Objects, E-SDO, Detached Objects, Distant Detached Objects, DDO, or Scattered Extended in the formal classification by the Deep Ecliptic Survey. The discovery of Sedna resurrected the question of which astronomical objects should be considered planets and which should not. On March 15, 2004, articles on Sedna in the popular press reported that a 10th planet had been discovered. This question was answered under the International Astronomical Union definition of a planet, adopted on August 24, 2006, which mandated that a planet must have cleared the neighborhood around its orbit. Sedna has a Stern-Levison parameter estimated to be much less than 1, and therefore cannot be considered to have cleared the neighborhood, even though no other objects have yet been discovered in its vicinity. To qualify as a dwarf planet, Sedna must be shown to be in hydrostatic equilibrium. It is bright enough, and therefore large enough, that this is expected to be the case, and several astronomers have called it one. Exploration. Sedna's perihelion will be reached around 2075 through 2076. This close approach to the Sun provides an opportunity for study which will not occur again for 12,000 years. Though Sedna is listed on NASA's Solar System Exploration website, NASA is not known to be considering any type of mission at this time.